Greetings. The Plastic Pipe and Fittings Association is pleased to offer this presentation of thermoplastic industrial piping systems, or TIPS. The presented material has been carefully prepared and includes the most technically correct information available. However, the information presented is a guideline only. For specific applications, consult with a knowledgeable product manufacturer, distributor, or an experienced professional engineer. The presentation is in 7 parts, including the introduction, features and benefits, engineering design considerations, joining, installation, testing, and repairing, product availability, selecting the proper plastic piping material, and applications. This presentation and other educational tools are readily available by contacting the PPFA as shown. The PPFA is a 3-decade-old organization whose mission is to educate, promote, and defend the use of plastic piping products in North America. Association members include processors, plastic processing equipment manufacturers, resin, compound, and additive manufacturers, and industry consultants. The TIPS product line committee is comprised of companies with a combined experience of over 300 years of manufacturing and processing expertise in thermoplastic industrial piping systems. Most thermoplastic piping is used for underground applications. Most of these applications have been excluded from this presentation, as well as other plastics that are non-rigid, not thermoplastic, or are thermoplastics combined with other fiber-type non-plastic materials. PEX and ABS, for the most part, have been excluded due to their lack of use in the North American industrial market. To benefit most from this presentation, be open to and inquisitive of new piping ideas and concepts. The word plastic is derived from the Latin word plasticus or the Greek word plastikos. Both mean the same, to mold or shape. There are 2 major plastic categories, thermoplastic and thermosets. Thermoplastic piping includes, but is not limited to, vinyls, PVC and CPVC, polyolefins, polybutylene, polyethylene, and polypropylene, fluoropolymers, polyvinylidene fluoride, and ABS. Thermoset piping includes, but is not limited to, phenolics, reinforced epoxies, polyesters, vinyl esters, and reinforced thermoplastics. Whether the plastic piping material is a polymer, copolymer, or tripolymer, the building block of most plastics is the monomer. Chemists, using pressure, heat, and additives, form monomers into chains of carbon and hydrogen-rich formulations, producing the desired resultant plastic. Most thermoplastic piping resins are made from feedstocks of oil and gas. These carbon and hydrogen compounds are combined with elements such as chlorine, fluorine, nitrogen, and oxygen to form a particular plastic. All of the resin's elements are chemically bonded and cannot be disconnected by any exterior forces. Each plastic compound manufacturer is like a chef preparing a generic entree. The entree is recognizable and made from a common base, but by adding seasoning or additives, each has a slightly different taste or performance. Each group of plastic compounds must adhere to rigorous standards as listed by the American Society of Testing and Materials International. Therefore, the compounds, although slightly different, must share many similar physical characteristics. The plastic extrusion process is similar in principle to using a cornucopia-shaped bag filled with decorative icing. When the exterior of the bag is squeezed, the icing is forced through a nozzle or die into the desired shape and diameter. Thermoplastic piping is extruded in diameters from 1/8 inch to several feet, mostly in lengths of 10 or 20 feet. An automatic pipe cutter downstream of the extruder is adjustable for any shippable length requirement. Injection molding is similar to an automated cookie cutter, except, unlike cookie making, the plastic material is forced in the mold cavity under pressure and high temperature. Most thermoplastic fittings and valves are injection molded in sizes from quarter inch to 12 inches and larger. Extruded pipe and rod are used to fabricate non-injection molded fittings. Rotationally molded and vacuum forming are forms of plastic processing used mostly in large thin-wall products such as tanks and large filter or heat exchanger housings. This diagram represents a typical injection molding process. The hopper loads the plastic compound in the heated barrel, which houses a specially designed rotating screw. Additional heat needed to melt the plastic is generated by friction caused from the auger action of the screw. The heated plastic material is transported into the mold situated between the stationary and moving platens. At the desired time, molten plastic material is forced into the mold to cool before the movable platen retracts. The molded part is now ready to be automatically released. The spring-loaded ejector pins push out the finished product from the mold. The mold is closed by the movable platen to begin the injection process again. The process starts anew. John Hyatt discovered the first man-made plastic, cellulose nitrate, in his search for a replacement for ivory used in the manufacturing of billiard balls. From this auspicious start, thermoplastic piping has become the preferred piping material in many markets, such as underground sprinkler systems, acid waste drainage, residential drain waste and vent, ultra-high purity water, gas distribution, water mains, sewer pipe, swimming pools, and several other applications. The American Society for Testing and Materials, ASTM, is a national standards organization that develops and provides standards for most thermoplastic industrial piping systems. The National Sanitary Foundation International, Canadian Standards Association, or IAPMO are frequently used as a third party to certify these standards are met and maintained by inspecting products and plant manufacturing sites. Almost all thermoplastic piping, fittings, and valves, unlike other non-plastic fluid handling products, are clearly marked to designate the type of plastic material used in manufacturing. These external designations assure the engineer, installer, and user of product compatibility and adherence to published standards. Many of the older ASTM pipe designations were 4 digits and are still used in some piping products. Many of the newer piping ASTM designations are referred to as cell classifications consisting of 5 digits. Cell classes better define the plastic material compared to the older classification. This presentation includes mainly the listed thermoplastic material designations. Manufacturers of thermoplastic piping compounds have slightly different formulations, resulting in slightly different physical properties. The values shown are estimates and could range plus or minus 5% or more. Thermoplastics have the lowest specific gravity of any piping materials. Polyolefins have a specific gravity of less than water, which may allow these piping materials to be uniquely installed in underground water applications. Tensile strength, or breaking load, and tensile modulus of elasticity of the material are influential in determining the long-term pressure abilities of thermoplastic piping. The modulus of elasticity affects the stiffness of pipe and is normally represented by stress-strain curves at any given elongation point on the curve. The flexural strength and flexural modulus of a material decides the pipe's stiffness. That affects support spacing and resistance to earth loads in buried piping. The resistance or mechanical energy absorbed by a plastic on impact determines the outer toughness of piping products. Due to a larger coefficient of thermal expansion, thermoplastics expand and contract at a greater rate than other piping products. Almost all thermoplastics, when compared to other piping materials, have much lower thermal conductivity, resulting in reduced or no need for piping insulation and significantly reduce the possibility of developing condensate or sweating on the pipe exterior. The tensile strength and pressure ratings of thermoplastic piping decrease with an increase in temperature. These pressure-temperature relationships are calculated and listed in engineering tables. Most thermoplastic piping materials have an ability to resist abrasion and erosion much greater than most other non-plastic piping systems. Plastic ignition temperatures are 200 degrees Fahrenheit higher than wood products. In no case can plastic piping materials flash or self-ignite until temperatures approach 650 degrees Fahrenheit or higher. Vinyls and fluoropolymers will not support combustion. Polyolefins are less resistant to Underwriter Laboratory and other agencies' flammability testing. The limiting oxygen index, LOI, is another method of determining which materials burn easier than other materials. For example, cotton requires an LOI of 16, while CPVC and PVDF have an LOI of 45 to 75. Flame spread and smoke development indices are material characteristics of plastic piping systems determined by third-party testing agencies. Most North American building and mechanical codes require combustible piping in return air plenums to have a maximum flame spread value of 25 and a maximum smoke development value of 50. It's advisable to contact plastic piping systems manufacturers to determine the flame spread and smoke indices of their products if used in air plenums. In addition, there are a few companies that offer specialty products that can improve and may meet flame spread and smoke development requirements. Thermoplastic industrial piping systems are environmentally sound, easy and safe to install, reliable, long-lasting, and cost-effective. Thermoplastic piping has over 6 decades of proven performance worldwide in a multitude of applications, and many of these installed piping systems may last a century or more without any decline in performance. The chemical resistance of thermoplastic piping is one of the major reasons plastics have replaced other non-plastic piping materials in industrial applications. Galvanic and electrolytic corrosion is not a factor or concern with any thermoplastic piping material. The extrusion and injection molding processes used in manufacturing thermoplastics leave an extremely smooth interior finish on all of its piping products. Whether it's pipe, fittings, valves, or other fluid handling products, thermoplastics are one of the lightest weight piping materials available. Most thermoplastic piping materials are much more abrasive resistant and erode less at higher velocities than other piping materials. Thermoplastic piping has low thermal conductivity characteristics, which allows greater temperature retention of the fluid being transmitted. The physical characteristics of thermoplastic piping allows the installer and designer multiple of options in joining techniques. Almost any color pipe imaginable can be extruded. Several markets such as drainage, sewer, water distribution, gas distribution, reclaimed water, and others have distinct colors for easy identification. Piping flexibility varies with each thermoplastic material. This feature allows underground plastic piping to be easier to install and more cost-effective while providing excellent performance. Pigmented thermoplastic piping is usually more weather-resistant to ultraviolet degradation than clear or unpigmented pipe. An easy-to-apply approved pipe coating will prevent the effects of any long-term weathering. Once the thermoplastic internal piping is properly joined, cleaned, and purged, there is no toxic contamination or noticeable odors. Using proper bagging, storage, handling, and cleaning of thermoplastic piping, there is no significant biological or bacterial presence or invasion in the interior or exterior of the pipe wall. There are more than a dozen national and international codes or standards which ensure manufacturing accountability for product performance. This also allows for interchangeability among similar manufacturers' products. Thermoplastic piping products are available in an entire fluid handling system, including pipe, valves, fittings, tanks, pumps, sheet, rod, duct, fans, scrubbers, and heat exchangers. In most cases, other piping materials have no need to come in contact with any of the transported fluids. Using hot air welding techniques, heat fusion, machining, and other fabrication methods, almost all thermoplastic piping materials can be used for specially designed products. Almost all thermoplastic extruded and molded piping products have easy-to-read identification markings on the exterior surface of the product. Thermoplastic piping systems are notably friendlier to the environment than other piping products. Completed and ongoing life cycle assessment results are scientifically confirming that plastic piping is second to none compared to other piping materials when it comes to environmental impact. Most thermoplastic fluid handling products are readily available from a distributor's or manufacturer's inventory. Special engineered or unique configurations, when needed, can be provided in a timely manner. The bottom line of why thermoplastics should be considered by design engineers, contractors, and end users is they are very cost-effective on an installed basis versus other piping materials. Escalating transportation, insurance, and maintenance costs, plus job site thefts, should be a consideration when deciding which piping system to use. Proper pipe design is essential for all industrial applications. All successfully installed piping systems include generally accepted engineering piping practices, transcending any particular piping material. The relationship and limit of temperature, pressure, thermal expansion, and pipe supports are considerations that must be understood to properly design and ensure a successfully engineered industrial thermoplastic piping system. A major reason thermoplastic piping is considered for industrial applications is its chemical resistant capabilities. This applies to both the fluid being transported and the outside environment. About 1,000 different chemicals and solutions have been tested by plastic resin and product manufacturers to assist designers and users as to which plastic piping material to select. In addition, chemical resistant tables are available for elastomeric compounds such as gaskets and O-rings that are used in sealing plastic flanges, valves, and pumping products. Although years of experience and testing have gone into the published chemical resistant data, it is highly recommended that designers and users verify these fluids for material compatibility. Most thermoplastic piping used for TIPS applications is made to ASTM standards and is pressure rated for water at 73 degrees Fahrenheit. This is based on the Plastic Piping Institute listed hydrostatic design basis, HDB, multiplied by a design factor to yield a hydrostatic design stress, HDS. For example, vinyl piping has an HDB of 4,000 psi and a design factor of 0.5, which gives an HDS of 2,000 psi. Iron pipe size, or IPS, dimensional pipe is available in Schedule 40, 80, and 120. In schedule piping, the pipe wall thickness matches that of steel pipe. This results in pressure ratings that decrease as the pipe size increases. There is also a standard dimension ratio, or SDR pipe, commonly available. This SDR system was developed to have consistent pressure rating of all pipe diameters for a given material. The ratio of pipe outside diameter to pipe wall thickness is the dimension ratio, or DR. Most metric size piping is constant pressure rated, similar to SDR piping. SDR piping is commonly used for non-industrial thermoplastic piping applications, such as irrigation, water mains, sewerage, and gas distribution, although in some cases the outside piping diameter could be dissimilar to schedule pipe. Metric size piping is usually manufactured and used in countries outside of North America. However, several unique metric piping systems are used in the USA. The different diameters of metric and IPS or SDR pipe greatly reduce chances of mixing components from both systems. Always be aware of the product standard and markings on the pipe. Some vinyl fitting manufacturers have derated the operating pressure of their fittings as compared to the operating pressure of the pipe. Therefore, in critically sensitive pressure applications, it is highly recommended to check with the fitting manufacturer to determine the exact operating pressure capability of their molded and fabricated fittings. In some non-industrial piping products, sewer pipe and others, there are differing outside pipe diameters and pressure ratings available in addition to the schedule and SDR piping. Knowing the relationship of the temperature and pressure of the fluids being transported by thermoplastic piping is critical for a successful installation. The rule in thermoplastic piping is, as the operating temperature of a fluid increases, pressure rating of the thermoplastic pipe decreases. The working pressure of Schedule 40 and 80 thermoplastic piping mostly decreases as the pipe diameter size increases. Temperature correction factors for derating the working pressure of thermoplastic piping are available from the manufacturer. In the example shown using manufacturer-published tables, it is easy to determine the maximum pressure rating for any application. Thermoplastic valves, unions, and flanges tend to limit the pressure in a thermoplastic piping system. For many of these products, 150 psi is the maximum working pressure rating at ambient temperature. Some products, valves in particular, may have higher pressure ratings, but to be sure, check with the manufacturer. As with pipe, the working pressure of valves, unions, and flanges must be derated as temperature increases. Each manufacturer might have slightly different temperature correction factors for their products. Check with the manufacturers. Pipe threading decreases the working pressures of all thermoplastic piping. Where possible, avoid direct threading thermoplastic pipe. In almost all thermoplastic piping applications, collapsing of pipe walls from a vacuum or negative pressure is not a major consideration. Almost all thermoplastic piping products have had their pressure loss calculated and listed using the Hazen and Williams formula. Friction losses are usually lower with plastics than other piping products. The example shown uses the formula to calculate the friction loss through a valve. Knowing the pipe diameter and flow rate, the velocity and friction loss can be calculated. Friction loss tables are available for most pressure-rated thermoplastic pipe, fittings, and valves. In the example shown, it is a simple task to determine the friction loss in feet or psi. Common thermoplastic piping materials have a friction loss coefficient, or C factor, of 150. This factor for thermoplastics is higher than most other piping systems and normally maintains its value throughout its use. The end result is there is less friction loss in thermoplastic piping compared to most other piping systems. With proper design, the engineer can minimize the effect of hydraulic surge or water hammer. However, it is prudent to calculate this possible event, especially if the fluid velocity is higher than 5 feet per second and there are pumps, valves, and long runs of pipe. To determine if the pipe working pressure is capable of handling the surge, we must add the surge pressure to the line pressure. In this example, the total pressure of 250 psi is well under the maximum working pressure for this piping application. To avoid hydraulic shock, incorporate the same design principles as in other non-thermoplastic piping systems. The thermal expansion and contraction of thermoplastic piping is a significant factor and must be considered with plastic piping systems. Plastics expand or contract more than most other piping materials. Engineers must calculate and design for these changes in pipe length. Using the listed formula and knowing the material Y value plus the conditions of service, calculating the total pipe movement is easily done. Based on the plastic material's modulus of elasticity and coefficient of thermal expansion, constant factor values Y have been calculated for all plastic piping materials. The larger the Y value, the greater the expansion and contraction. Managing the expansion and contraction of thermoplastic piping systems is similar to other piping systems. Like other piping systems, expansion lakes or loops are the preferred methods of handling this phenomena. Fabricated or bellows type expansion joints can be installed, but should be used as a last resort because of increased maintenance, lower reliability, and at usually increased cost. Using the expansion loop formula, the loop length may be calculated based on the conditions of service, piping material, and piping diameter as shown in this example. Thermal stress can be easily calculated in restrained thermoplastic piping applications. In many cases, plastic piping may be able to absorb the thermal stress within the pipe, therefore, not requiring any expansion products or design changes. In the example shown, the pipe stress of 324 psi in this restrained environment is well within the pipe's working pressure capability. The longitudinal forces generated in thermoplastic piping are normally much less than metal piping systems due to lower thermal stresses of plastics. This means a metal pipe could generate enough longitudinal force in a restrained system without proper design for expansion to break brick walls, while plastic pipe, under similar conditions, would tend to bend or fail without affecting the restraining barriers. In this example shown, 504 pounds of longitudinal stress was developed. For most applications, thermoplastic piping systems require more piping supports than other systems. If piping supports or clips have rubber in contact with the pipe, it is prudent to make certain the elastomer is compatible to the piping material. The number of pipe supports for thermoplastic piping decrease as the pipe diameter increases. Pipe support spacing is affected by the specific gravity and temperature of the fluid being handled. Heavier fluids and elevated temperatures will frequently require more support. Although thermoplastic piping systems require more pipe hangers, the hangers are lighter in weight than those used with other piping materials. If higher temperatures require excessive hangers, the use of a continuous metal V-channel or half-round metal piping may be used to minimize the number of hangers. The proper installation of pipe anchors and guides are critical for above-ground piping systems in which significant expansion and contraction can occur. Not only is the proper anchor and guide material important, but equally important is the placement of each anchor and guide. Heat loss in metal piping is about 200 to 300 times greater than that of plastic. Therefore, plastic piping requires less insulation than metal piping systems. To calculate the heat losses of any piping material, use the listed equation. In the example, PVC had a heat loss of 273.5 BTUs. With similar conditions of service and pipe diameter using steel pipe, the heat loss of 73,248.8 BTUs is almost 268 times as much as PVC. The tensile strength of thermoplastic piping increases and the shear strength decreases when the temperature is lowered. Low temperatures increase brittleness of the piping. When handling thermoplastic piping in cold weather, be careful of sharp impacts to the piping. Some thermoplastic piping materials can handle cold operating temperatures better than others. Material selection and pipe protection is important in these situations. Most thermoplastic piping has a more limited range of temperature capability than other piping materials. Expansion, contraction, working pressure, support spacing, and chemical compatibility must all be considered as operating temperatures change. Ultraviolet radiation can cause a noticeable change of color to the outer wall of thermoplastic pipe, but in most cases not causing any reduction of the piping performance. If using thermoplastic piping outdoors for an extensive period, coat the pipe with a manufacturer's recommended material. Do not use any thermoplastic piping in transporting of or in testing with compressed air or gases. The one exception is the use of polyethylene gas piping and other specially formulated plastic compounds specifically designed to handle compressed gases. Always follow the manufacturer's instructions. The design considerations for buried plastic piping vary by material and in some cases by manufacturer. Always follow the piping manufacturer's installation and design instructions. The manufacturer of pipe can provide pipe stiffness values for each of their products. As in pipe stiffness values, manufacturers publish bearing instructions regarding soil stiffness and pipe loading. Trenches for thermoplastic piping should be as narrow as possible to improve the pipe integrity with the compacted soil. See the listed table and check with the pipe manufacturer for additional information. Pipe burial depth is a critical design consideration based on ground traffic and geographic location with thermoplastics as well as other non-plastic piping systems. Thermoplastic joining, installation, testing, and repairing techniques are quite similar to non-plastic industrial mechanically joined piping systems. The two major joining systems in thermoplastics that differ from other piping systems are solvent cementing and heat fusion. Here we will explain the many proven techniques used for successful thermoplastic industrial piping system installations. Generally accepted industrial piping practices apply to thermoplastics and all other piping systems. When installing plastic piping systems for the first time, it is strongly recommended that for and the responsibility of the contractor to thoroughly train their crews before starting the construction project. Before installation, all piping materials must be thoroughly inspected and cleaned. When cutting plastic pipe, use the proper tools and deburr the pipe ends, especially when joining solvent cemented and heat fused pipe into socket fittings and valves. It is important when joining plastic pipe: 1. To keep dirt and grime from the joining products. 2. Keep products to be joined at similar temperatures before joining. And 3. Follow completely the manufacturer's joining instructions. Before installation, all piping products should be thoroughly inspected for cracks or gouges. If these irregularities exist, remove the damaged parts completely. The use of flanges allows dissimilar piping materials to be joined to one another and is especially useful for installing larger diameter pipes. Flanges also allow complex piping systems to be prefabricated in a controlled environment and then shipped to the job site. Flanging plastics is very similar to other flanging piping materials. Consider flanging when joining above ground large diameter piping and joining dissimilar piping materials. The growth of ABS, CPVC, and PVC piping systems is mainly due to the ease of permanently, quickly, safely, and cost-effectively joining these materials. A minimum investment of inexpensive installation tools is required. Solvent cemented joints are chemically bonded and will have cross-sections showing a homogeneous and monolithic bond. If using a brush for cementing, make certain that it is a natural Bristol type and with a width of approximately half the pipe diameter to be joined. Work gloves, eye protection, and a well-ventilated area are safety procedures that should be practiced. The joining instructions for solvent cementing are shown in manufacturer's instructions as well as in ASTM D2855. Follow the instructions completely, taking no shortcuts. The polyolefins, polybutylene, polyethylene, and polypropylene, and most fluoropolymers piping systems are easily joined using heat fusion to produce a joint similar to solvent cementing. The heat fusion joint is permanent and cost-effective while being able to withstand the same or higher working pressure of either piping product being joined. Butt fusion is the most common heat fusion joining system. When butt fusing, make certain the proper joining tools are used. Keep pipe ends squared and in alignment. Ensure the proper pipe heating time with the hot plate and the proper heat soak time when joining the heated pipe ends. Do not take shortcuts when joining and follow completely manufacturer's instructions. For butt fusing large diameter piping systems, 10-inch and above, consider using companies that have special automated tooling and offer experienced field personnel who will make up the joints or supervise the installation. Butt fusion joining equipment can be purchased or rented. Infrared radiant fusion piping joining is relatively new and used when minimum or no metal extraction or leaching can be tolerated in the fluid system. The high-tech joining method was developed primarily for the semiconductor industry in their pursuit of the highest purity water levels. The joining illustrations show that the pipe ends to be joined never come in contact with the heating element, but rather are heated by radiant heat. Once the heat source is removed, the pipe ends are brought together and held for the proper heat soak time, similar to butt fusion. Infrared joining machines are quite expensive, and depending on the size of the project or the number of projects an installer will be involved with, outright purchase or rentals of the machines are options. Bead and crevice-free joining systems were developed for piping requiring a minimum of bacteria-free buildup and optimum flow. Ideal for the semiconductor, pharmaceutical, and food and beverage industries. The joining process is similar to butt fusion, except a balloon is inserted in the joining area before joining the heated pipe ends, preventing an internal weld bead to be formed. This joining system is used mostly in smaller diameter piping systems. The joining machinery is sophisticated and expensive. It would be prudent to use an experienced crew or supervisor to assist in these installations. Socket heat fusion joining systems have been successfully used for over 4 decades. Socket fusion requires heating the pipe OD and the fitting socket, then assembling while the material is still soft. The heat soak time can be visually controlled by observing the diameter of the bead against the heating tools. The final joint will have a similar size bead as in butt fusion. This joining system is ideal for pipe diameter 6 inches and below and for close quarter installations. As in all heat fusion joining methods, be conscious of working with the hot plate. Insulated gloves should be used for safety reasons. Electric fusion joining has been in use for many decades in joining polypropylene, polyethylene, and polyvinylidene fluoride chemical waste drainage systems. The system is automated and takes the guesswork out of heat fusion time. In many cases, more than one joint can be made at one time. Do not clip off the pigtails until the system is tested. In case there is a small leak, the pigtails can be reattached and additional heating provided. Electric fusion joining systems are used in many low-pressure chemical drainage applications. On large projects, an entire system can be dry-fitted and then fused. Fusion machines can be purchased or rented. Mechanically joined grooved-end piping systems can either have cut or rolled grooved pipe and an elastomeric gasketed metal coupler. The advantages are similar to flanging. That is, one can join or disjoin piping materials and prefabricate an entire piping system for shipping to the job site. Due to material characteristics, this system is recommended for vinyls and not for polyolefins. Several pipe suppliers can supply groove pipe ends to simplify and reduce labor requirements. Check with the piping system provider to determine if there will be any derating of the pipe working pressure. Also, make certain that the coupling elastomer is compatible to the fluid being handled. Grooving machines can be purchased or rented. This mechanical joining system is similar to the cut and rolled groove system mentioned before. However, instead of a metal coupler, a plastic coupler with plastic splines are used. To date, only PVC piping is used for this joining method. The two advantages of this system is the removal of any metal coming in contact with the fluid being handled, and the lack of any expensive joining tools. There are presently two manufacturers who provide this type of joining system. Make certain that elastomeric seals are compatible to the fluid being handled. This joining system is mostly used for 12-inch diameter and below. The final groove joining system to be discussed is a cut groove system used primarily for underbench polypropylene and polyvinylidene fluoride chemical waste systems. This system has similar advantages of other groove systems. In addition, there are no expensive tools, no electric sources needed for joining, and it is easy to install. Make certain the spanner wrench is plastic as supplied by the piping system manufacturer. This joining system is used mostly for 1.5-inch and 2-inch piping systems. Do not use this joining method for underslab or in-wall applications. The larger diameter drainage piping is permanently joined using heat fusion or solvent cementing techniques. Although this joining system is used for rigid piping systems, there are many more applications using push-fit joints with flexible tubing. Be certain, when using this joining method, that the elastomer and gripping ring are fluid compatible. The quick connect and disconnect system of joining has been successfully used in industrial applications for over 3 decades. It has similar advantages and limits as the push-fit joining system, except this system can go up to 4 inches in diameter. The present materials being offered with this system are glass-filled polypropylene and polyvinylidene fluoride. If you must use a threaded system in thermoplastics, the use of transition fittings should be considered. These fittings allow thermoplastics to be joined with metal piping systems, minimizing many engineering design concerns that might occur when directly threading plastic piping to metal connections. The additional cost of using transition fittings more than offsets the possible lack of joint integrity with the direct threaded pipe. The two limitations of this system are a maximum 150 psi working pressure and sizes up to 3-inch diameter. Direct threading of Schedule 80 or 120 thermoplastic piping is not the optimum system to use if joint integrity is a must. Schedule 40 and many SDR piping should not be directly threaded. However, if a threaded system is required, use pipe threading dies designed for plastic pipe threading. To obtain a proper seal, use an approved Teflon paste or tape for the finished thread. The maximum diameter pipe to be threaded should not exceed 4 inches in diameter. Direct threading reduces the working pressure of vinyls by 50% and is recommended for drainage applications on other plastic piping materials. If threading is definitely required, use transition fittings wherever possible. For industrial applications, use threaded plastic joints only if absolutely necessary. When tightening plastic to plastic threaded fittings, use a strap wrench and do not over-tighten. The key to any successful installation of an industrial piping system is to use experienced and knowledgeable pipe fitters and/or plumbers. There are experienced personnel available to instruct a novice crew of the proper installation process. Many manufacturers and distributors will provide this service without cost. The storage and handling procedures for plastic piping is similar in many ways to other piping systems. Thermoplastic piping is not fragile, but the installer needs to incorporate preventive measures to minimize breakage, cracking, or surface weathering. Having an experienced installation crew who completely follows all, and I repeat all, of the manufacturer's recommendations is a sure way to have a successful piping system. Listed are 9 highlights to consider when installing an above-ground plastic piping system. The majority of plastic pipe is buried due to the many aforementioned features and benefits. Listed in the summary of points to remember are 8 highlights to consider when installing an underground plastic piping system. Unless a manufacturer very clearly and specifically states differently, thermoplastic piping must be tested hydrostatically only using normal pipe testing procedures and must not be tested with compressed air or gas in any manner. Testing with compressed air of certain plastic piping materials can result in severe property damage and loss of life. When a thermoplastic piping system is properly installed, there is little likelihood that repairs or future maintenance will be required. If maintenance is required, use standard repairing techniques. If very small leaks occur in solvent cemented or heat fused joints, back welding by an experienced welder may be capable of providing a successful repair. Make certain before beginning back welding that the joint area is moisture free. The diameter of the welding rod and the number of weld beads depends on pipe diameter size. Use standard repair methods for threading, flanging, and other mechanical joints. Inline repairs of solvent cemented or heat fused systems should only be implemented if there are very small leaks. If larger leaks occur, remove the entire leaking joint and replace with new piping products. There is a broad range of thermoplastic piping products presently available, with additional products constantly being introduced. There are more products and greater size ranges available than are shown in this presentation. The size ranges shown for the piping materials include extruded pipe and molded fittings, generally up to 12-inch diameter. Larger size piping and fittings may be available as fabrications from pipe or sheet. Larger size acid and chemical waste drainage systems are fabricated from existing extruded pipe. Neutralization tanks of similar piping materials are generally available. It is absolutely essential to use only special formulated thermoplastic piping materials for compressed air and gas applications. In other cases, most manufacturers do not recommend the transportation or testing of compressed air or gas in their piping systems. Double contained piping systems are very versatile. The carrier and containment pipe can be made with similar or differing materials, including combinations of thermoplastic and non-thermoplastic. Leak detection devices, pump and valve enclosures, and double containment tanks are also available. Almost any non-plastic valve style is available in one or more thermoplastic materials. Usually these valves can be offered with manual, electric, or pneumatic controllers. Basket and Y strainers are molded or fabricated in many sizes and many materials. Filters are available for the most demanding filtering requirements in 4 different thermoplastic materials and various filtering elements. Like plastic valves, thermoplastic pumps are available in types and size ranges similar to the non-plastic pumping styles. Thermoplastic sheets, usually in sizes 4 feet by 8 feet and from 1/8 to 2 inches thick, are available in the same materials as pipe. Rod and other extruded profiles in pipe materials are available from 1/8 inch to 6 inch diameters. Extruded and fabricated ducting, fans, and dampeners are available in most thermoplastic piping materials. Thermoplastic scrubbers are usually fabricated. Injection molded scrubber packing is available in many different shapes and thermoplastic materials. Most rotationally molded tanks are available in polyolefin thermoplastics. Fabricated tanks are available in all thermoplastic materials with exterior shells of the same or different materials. Using hot air welding and machining techniques, a competent fabricator can design and build almost any piping system component from any thermoplastic material in a very short time period. Several manufacturers of thermoplastic flow monitoring and control devices offer units made of varied thermoplastic piping materials. Standard and fabricated heat exchangers are available in several thermoplastic materials with various sizes depending on the application. There are many products readily available to join, prepare, test, and repair thermoplastic piping products for all materials and sizes. The proper tools will ensure construction projects with fewer problems and faster completion times. Having the necessary technical and pricing information available and knowing the conditions of service for an application, one can quickly and effectively decide which thermoplastic piping is appropriate and most cost-effective for the applications. The more one knows of the exact conditions of service for a specific application, the more likely the proper and most cost-effective piping material will be selected. There are 5 dominant material selection criteria to consider when determining the suitability and effectiveness of thermoplastic industrial piping materials. The example shows in bold type lists the 5 major conditions in selecting the proper piping material. Chemical resistance is first checked to settle on which plastic piping material, if any, can handle the designated fluid. However, be aware that many solutions are mixtures and all fluid components must be considered. The next step is to decide the ability of the plastic piping products to handle the pressure and temperature that is expected. Steps number 3 and 4 are to find out which piping products are available and to select the most cost-effective joining system. If more than one plastic piping system is appropriate, decide which one is most cost-effective. One other point not mentioned is to make sure the system selected is third-party certified by the applicable code if required. By slightly changing one or more of the service conditions in the example shown, other thermoplastic piping materials may be considered or eliminated. There are many successful industrial uses of thermoplastic piping systems worldwide. Listed in this section are 30 industry applications comprised mostly of the piping materials covered in this educational presentation. Thermoplastics have been the preferred and dominant piping material in acid chemical waste drainage for almost 3 decades, replacing glass and metal piping systems. An entire air pollution control system offering excellent chemical resistance and ease of installation is available, consisting of duct, fans, hoods, scrubber, and packing in all the common thermoplastic materials. Thermoplastics are used extensively in fountains, amusement, theme, and water parks because of their ease of installation, high flow characteristics, and ease of maintenance. Most of the modern aquariums worldwide have discovered the cost-effectiveness of using thermoplastic piping for both fresh and saltwater systems. In addition, specially formulated plastic compressed air piping systems are used for water tank aeration. Most plastic piping system manufacturers have chemical resistant tables available covering a multitude of different chemicals. Generally, thermoplastics are more chemically resistant than any other piping system. Thermoplastic piping handles most of the fluids and vapors found in the chlor-alkali industry, an application that comprises some of the most corrosive and chemically aggressive agents of any industry. Whether highway or bridge drains, high school or college laboratories, municipal dewatering systems, large diameter potable water systems, or fire sprinkler systems, thermoplastics have many proven years of success. Specially formulated thermoplastics are used in compressed air lines, especially when non-contaminated air is a requirement, such as painting and coating applications, hospitals, clean rooms, pharmaceutical plants, and food and beverage processing. Polyethylene piping has been used in gas distribution lines for decades. As the cost and unavailability of water escalates, the construction and use of desalination plants will escalate. Plastic piping is the preferred piping material in many of the present desalination processes. Double containment piping is simply a double piping system where the carrier pipe is centered and affixed to the inside of a containment pipe. This will prevent leakage from the carrier pipe into the environment. These fabricated and pre-assembled piping systems are constructed combining all plastic, all metal, or a combination of plastic and metal piping systems, depending on the conditions of service. Usually, there is a manual or automatic leak detection device accompanying the piping system. Few industries have adopted thermoplastic piping systems as aggressively as the electronic and semiconductor industry. Because of the highly corrosive chemicals and the water purity requirements of this industry, millions of feet of plastic piping are in use today in this high-tech industry. Thermoplastic piping systems are used in many single and double containment systems, preventing toxic materials from contaminating soil, groundwater, or other bodies of water, as well as causing direct harm to humans. Vinyls and polyolefin piping and pond liners are used in many landfill installations. There has been a broad acceptance by many code bodies in North America to include fire sprinkler systems as a standard feature in new homes. The majority of these systems will consist of either CPVC or PEX piping materials. Usually, CPVC piping is installed in standalone systems incorporating a separate piping system and water source. PEX piping is normally used in a multi-purpose system combining with an existing cold water plumbing line. Both systems are well tested and have proven to be very successful. When industrial fire hydrant piping is required and there is an aggressive soil condition, thermoplastic piping materials are most commonly used. Shrimp, catfish, salmon, bass, and other fish hatcheries and farms are experiencing double-digit growth each year. These industries use thermoplastic piping extensively throughout their processes. When properly installed and pre-cleaned before startup, thermoplastics are basically odorless and non-toxic, making them an ideal piping material for the food and beverage and pharmaceutical industry. Geothermal energy is becoming more of an energy option as oil and gas become scarcer and more expensive. This non-polluting energy source uses thermoplastic piping in many applications below 100 degrees centigrade. Slip lining of existing corroded concrete or cast iron municipal piping with thermoplastics produces significant cost savings. In addition, mechanically joined plastic piping systems are used in many large dewatering projects. Thermoplastics are used in many HVAC applications, but in no way are they specified to their maximum potential in this industry. The plastic piping industry needs to educate more thoroughly the HVAC design engineers. What better application for thermoplastics than a saltwater environment? Salt or fresh water has no harmful effect on plastic piping. With thermoplastic's lightweight characteristics, it should be the material of choice for several onboard and marina piping applications. The toughness, chemical resistance, and abrasive resistance of plastic piping make this the preferred piping material in many open and underground mining applications. For these same reasons, thermoplastics are used throughout the smelting and refining process of crude ores. In numerous areas of the oil and gas industry, plastic piping offers many advantages over other piping materials. The lightweight and durability of thermoplastic piping makes it an ideal piping material for use on manufacturers' equipment. Many skid and truck-mounted assemblers use plastic pipe, valves, fittings, tanks, and pumps wherever they can. The pharmaceutical industry uses thermoplastics, but not to the extent it could. Due to the features of odorlessness, non-toxicity, ease of joining, and lack of maintenance, thermoplastic is an ideal piping material for many pharmaceutical applications. Power plants are just now beginning to see the many possibilities of using thermoplastic process piping. This industry is a major user of large diameter plastic piping for intake water lines and other water and waste applications. There are many applications where thermoplastics are replacing stainless and fiberglass reinforced piping in the pulp and paper industries. Ice skating rink piping and refrigeration lines using brine solutions are prime markets for thermoplastic piping systems worldwide. It is ironic that the steel industry is one of the larger users of thermoplastic piping systems. Early on, steel plant engineers found that many cost savings thermoplastic piping provided in handling many of the acidic and corrosive conditions in steel processing plants. Surface finishing is another industry in which thermoplastics is the preferred piping material, especially for the transporting of metal salt solutions, corrosive vapors, and water treatment applications. Most indoor and outdoor swimming pool complexes incorporate thermoplastics throughout their piping systems. Waste and water treatment facilities are a large consumer of all types of thermoplastic piping materials. Few piping systems are as durable and cost-effective as thermoplastics for handling the changing technology of treating water and waste. Thank you for your attention and interest. In addition, the PPFA would like to acknowledge and thank those companies that contributed to producing this presentation. For more information on tips or other plastic piping systems, go to the PPFA website, www.ppfahome.org.